video, we are going to talk about Epsilon NFA, the NFA with Epsilon transition. The Epsilon NFA is same as that of the NFA. The only difference lies in the input symbols. That is, the reason for introducing Epsilon NFA is the following. Suppose if I want to move from one state to another state without scanning any input symbol. For example, when I want to construct an automata for representing both signed and unsigned numbers. So I think you know what the signed number, right? So signed numbers will start with the sign either minus or plus. But in case of unsigned number, it is not necessary for us to include the sign for the numbers. So in that case, in case of unsigned number, I want to move from one state to another state without scanning any sign, right? So in those cases, epsilon symbol, that is epsilon NFA, will be useful for us. It means that to move from one state to another state without scanning any input symbol, we can go with epsilon NFA. By addition of this extra symbol epsilon to the input does not increase the power of the epsilon NFA. Hence, the epsilon NFA is as powerful as that of the NFA. So the formal definition of NFA, epsilon NFA is same as that of the NFA. The only difference lies in the sigma, that is the input symbol. To the existing input symbol, we add the epsilon symbol. For the remaining parameters, it is as that of the NFA. Next, we come up with epsilon closure. Usually, we'll have a transition function. We start defining the extended transition function for dealing the strings. But here, to apply the extended transition function, we need to remove the epsilons present in the automaton. The function that is used for removing the epsilon values that is present in the automaton is the epsilon closure. So before we go ahead with the extended transition function, we'll see how to compute E-close for a particular state given in the automaton. So again, here we define epsilon closure recursively using mathematical induction, right? Assume that for the state Q, we want to find E-close, right? So in basis, for whatever state you are going to find E-close, we are going to include that in our answer, right? I'm repeating. If you want to find E-close for a state, say Q, by default we have to include that state in the answer, that is E-close of that state. In induction, suppose if some state P is already existing in the E-close of Q, and if there is a transition from state P to R on the input symbol epsilon, so then we have to include R also in E-close of Q. What do we infer from this? From state Q or for some state which is present in the automaton, if there is an epsilon transition from that state to some other state, then we have to include the destination state also. We will refresh this again with an example. Consider this example. So let us assume that we want to compute E-close for the states 1, 4 and 5. Right? Suppose first we will compute E-close for the state 1. As per the basis, for whatever state we want to compute E-close, we will include that state also in the answer. So here we are going to find E-close of 1, hence I have included that in the beginning. Next, from 1, we have to check for the transition on epsilon. So from 1 on epsilon, we have transition to the states 2 and 4. Hence, those two states can be included in our answer. Again, from 1, we have to keep on checking for this until we don't find any transitions on epsilon, right? So from 2, we have to check whether there is any transitions on epsilon. Yes, it exists, right? From 2 to 3, there is a transition on epsilon. Hence, it must be included. Again, from 3, we have a transition to 6. Next, it has to be included. And from 4, we have to check for all the possibilities. So from 4, since there is no transition on input symbol epsilon, we stop with this. But in case of 2, it keep on increasing. That is, it keep on including all those states which are reachable by scanning only the epsilon symbol. Right? Next, we'll go ahead with 4, the state 4. So whatever state you are computing E-close, that state has to be included by default, it is included. Then from that state we have to check whether there is any transition on the input symbol epsilon. So when we check for this example, we don't have any transitions on epsilon, on input symbol epsilon from state 4. So hence the E-close of 4 is 4 itself. Next we'll go ahead to the close of 5. So when I want to, as per definition, when we want to compute close of 5, we'll include the state 5 itself. Then from 5 we have to check whether there is any transitions only on epsilon. From 5 to 6 there is a transition, but it is on input symbol B, so it cannot be included. But from 5 to 7 there is a transition on input symbol epsilon, so it can be included. Thus E close of 5 is 5 comma 7, right? So now we know what is how to compute E-close. So with that we'll go for the extended transition function. We know what is extended transition function. Extending the existing transition functions for processing the string is known as extended transition function. When you observe this extended transition function, it is more or less same as that of your extended transition function of NFA. The only one thing that is different between these two automaton is the added E-close function. Yes, so that's it with Epsilon NFA.